And so that's kind of the idea of reference frames. And we'll come back and talk a little bit more about the importance of those, in particular, the importance of these so-called inertial reference frames. And again, we talked about those in Newtonian physics. Just a reminder, we'll see this later on, but an inertial reference frame is one that is not accelerating, okay? And I'm just going to say probably one of my only comments on this week, because I don't want to mix these things too much together in this class. We learned briefly on Thursday when we talked about general relativity. It's not anything you need to know about for this course, but we learned in general relativity that acceleration and gravitation are very much connected to each other. So you can imagine that the idea of inertial reference frames, okay, we're talking about special relativity, you can also imagine that it has strong and important connections to general relativity. I'm not going to talk about those because two confusing things in one go is too much, okay? And then in terms of observers again, how do we make observations? How do we describe things? We're going to use so-called standard clocks and standard rulers. And those are devices, and they're pretty much the things you would expect, that are defined to be at rest relative to the observer or the reference frame. So they're in the same reference frame. They are at rest with respect to the observers. So it's kind of technical, but simple. And again, because it's conceptually confusing, it's good to get the kind of precise things down. Okay, so what do we mean by saying that an observer is in a particular reference frame? Oh, shoot. Wow. I don't know what's wrong with this computer. I guess it has some weird problem with font recognitions. And strangely, there seems to be a theme of communication. Last week it was like mail, and now it's like telephones. Okay, let's see how we survive this. Okay, so an observer sets up, let's stick with a Cartesian coordinate system, x, y, and z as perpendicular coordinates in space. And we're going to set up clocks at every point in space to measure time. They're synchronized clocks. So once we've got our reference frame, it's just a flash. Let me see if it flashes. It does. I can, for any event at a particular point and time, I can make observations on it. And I can give it a stamp, a 4-dimensional stamp, in terms of the time at which an event occurred and the position in this 3-dimensional coordinate system, x, y, and z. So up there, where I don't have telephones and things, on the little cartoon, is a stamp on that event. So it's occurring at t, x, y, and z. Okay, so there's an observer in a well-defined reference frame. Let me say a little more about these inertial reference frames again, or inertial observers. Again, this is something we know. Actually, this concept went back all the way to Galileo. For us, up until now, we've kind of tended to describe inertial reference frames as ones in which Newton's second law, F equals ma, is valid. Okay? And you might remember fairly early on in the semester when we were talking about forces, I described some scenarios where you might see things in non-inertial reference frames that seem a little bit unexpected. And in particular, they don't seem to obey F equals ma. And so the examples that I gave at that time involved things like being on, I don't know, skateboards on accelerating subway trains or on aeroplanes or something. And so you have a pretty good idea already of the importance of inertial reference frames. So again, to reiterate, these are reference frames in which Newton's second law holds. There are other ways of describing it, but that's good enough. And for us, that means they are isolated objects that are either at rest or move with constant velocity. Okay? So just take a look at this very simple derivation down at the bottom. And it's looking at what Newton's second law looks like if I've got two reference frames. And one thing you'll see very often in special relativity, which doesn't help perhaps, though it's not obvious how to do it any differently or any better, you'll tend to see notations that look like this. So here's, for example, a velocity measured in a certain reference frame. Velocity is a function of time. And now this is the velocity with a primed notation, and that's very common in special relativity, in some different reference frame, and again as a function of t. These two reference frames are related simply by moving relative to each other at a constant velocity, big V. Okay, so a pretty easy transformation between this reference frame and this reference frame. Constant velocity difference between them. So if I apply Newton's second law to this so-called primed motion, primed reference frame, you can do your usual substitution here and just plug in the definition of the velocity in this reference frame compared to in this reference frame. And of course, you'll find out that Newton's second law remains valid. So these are both inertial reference frames. They happen to be moving a constant relative velocity with respect to each other. Okay. Another example of a non-inertial reference frame. This we haven't talked about, I don't think, in class so far, because it's talking actually about an accelerating reference frame that's not accelerating along a straight line, but it's actually accelerating by moving in a circular way. We do know that a circular motion, maybe even constant velocity circular motion, is acceleration, so here's an example of it. So what is this supposed to represent? It's supposed to represent the motion of an object, this black ball, as it's launched, let's say, from the center of a rotating reference frame. And so what you're looking at on that cartoon on the right-hand side is what the motion looks like in, firstly, up above, an external reference frame. So that thing, that disk is rotating, but from the outside perspective, the upper thing is showing you what that looks like if you're looking from the outside. And then down below is the representation of what it looks like if you're actually sitting in that rotating reference frame. Okay? So if you like, you can imagine this as actually being something physical that's rotating, maybe one of those things you might find in a fairground or in a kid's playground. It's something that's rotating, and just imagine what a ball thrown, let's say, radially outwards from the center of one of those rotating objects. Imagine what it looks like in terms of its motion from the perspective of an outside observer versus an observer that's sitting in that rotating reference frame. And of course, they're different. And in the lower case, where you're sitting in the rotating reference frame, this object is thrown. Of course, it's going in a straight line from the perspective of an external observer, but you are rotating, so it looks as though it's deviating off in the other direction. So this is the source of what are often called pseudo-forces. You imagine if something's accelerating in your reference frame, there's a force. But of course, there's no identifiable force here. Let's forget about gravity and projectile motion. It's simply that you're in a different reference frame. So this idea of pseudo-forces very much goes along with accelerating reference frames. You don't need to know about that for this course. This is a particular example for rotating reference frames, and for any of you who know about atmospherics and motions of air, fluids, and water fluids on the Earth's surface, you know that this is an important effect. And the Coriolis force, Coriolis effect is very much related to this. That's just an FYI. I don't care if you know that or not. Just illustrating the importance of inertial versus non-inertial reference frames. All right. So with a little bit of context in reference frames, let's turn our attention directly now to special relativity and the two and only two postulates. And so the two things that are on this slide are the only two things you need to develop special relativity. And of course, we have Einstein to thank for this, a master at thinking about things in unusual ways, not constrained by human experience. And so here are the two hypotheses, or postulates, if you will. So this is what now, 113 years ago? So it's been around for quite a while, even though we still tend to think of it as kind of modern physics. So what are the two postulates? First one, probably not too disturbing, because we kind of assumed it all along. Namely that physics is the same in all inertial reference frames. So it's a little bit of a limitation. So we have to be looking in non-accelerated reference frames, but provided we are, we expect physics to look the same, always. And so you can think of countless examples of this, and we talked about this when we talked in particular about relative velocity early in the semester, of scenarios where, you know, two objects moving or two systems moving relative to each other, constant velocity, but the systems themselves are moving, let's say, at some constant velocity. The ambiguity in sort of saying who's moving, who's not moving. Again, you have experience of this when you're on the subway, trains moving past each other, all these sorts of things. So first postulate is that physics is the same in all inertial reference frames. Note this is very specific. It doesn't talk about accelerating / non-inertial reference frames. And then the second postulate, and it's very concise, but the wording, as always, is important. All inertial observers measure the same speed of light, in vacuum, if you will, independent of the motion of the light source. In fact, a corollary to that might as well be independent of the motion of the observer, but this is sufficient. So that's a single sentence, but actually has enormous implications, okay? And that's sort of a radical new thing in special relativity. In particular, that last phrase, independent of the motion of the light source, and you'll see what I mean by that in just a moment. Okay, so let's look at this with a kind of example. And the reason I tend to use slides when I'm talking about special relativity and about general relativity is it's something that is very much helped by kind of cartoons and following the sort of thought experiments that Einstein did, which we'll be doing in a couple of minutes. So cartoons are kind of useful. So let's talk about this second postulate and ask how this differs from what our daily experience is, Newtonian mechanics. And so what I'm going to ask you to think about is simply an object that is moving. It could be that this is an oncoming car, it's coming towards us, is us as an observer, and we've got a car coming towards us. Okay, so here it is. And let's say we're imagining that that car is moving at speed c. Don't worry about what c is exactly right now. But what I want you to think about now is how that would appear if instead of being observer O, you're now observer O prime. Again, this is standard notations, just a different reference frame. But now I'm in a reference frame that is moving towards this oncoming car with a certain constant velocity v. Okay? So if that was us and we were kind of imagining this in our Newtonian / Galilean perspective, you would probably expect to, well, let me ask you, what would you expect if you were an observer in this O prime reference frame? You're moving towards this object with a speed v, it's coming towards you with a speed c. And the choice of c here is just suggestive rather than specifically necessarily being the speed of light. What would you expect to be the apparent approach speed of that car if you're in that prime reference frame? Right. So again, think of this in Newtonian slow motion experience. Your apparent relative speed of converging on each other would be the sum of these two speeds. Okay, so that's our Newtonian everyday experience. This is not true if indeed this thing is coming towards us, whatever it is. In fact, it's a beam of light. Okay, so that's why C, of course, was used in this case. If this is a beam of light, a wave of light, or a particle of light, we'll talk about that in the second semester, for those of you doing the second semester. If this is light, that's not what we see. We still see that light is coming towards us at the same speed, same velocity of light in vacuum, regardless of the motion. Regardless of the motion of the source, regardless of the motion of the observer. this information, this signal always comes towards us at the same speed. Really strange, right? I mean, you could imagine taking this to an extreme, and in fact say that you're moving towards this thing with a very large speed, maybe as large as the speed of light, and still it seems that this thing is heading towards you at the speed of light. Or even worse, maybe, I don't know, depends on how your intuition goes, you could be going away from this and it's still coming towards you at c, okay? So it's like you're being chased by something you can never quite get away from. So this is what's new about special relativity, and specifically the light travel speed. It is always c. All right, so more weird things coming up here. I want to talk a little bit about the history of this, not only because it's historically of interest, but because it actually has some relevance for something I told you about last Thursday in gravitational wave detection. So, let's see, special relativity, 1905. In the spring semester, we're going to spend most of the time talking about electromagnetism. In the mid-1860s, Civil War era, I guess, electricity and magnetism were unified into electromagnetism by Maxwell. And one of the immediate predictions of that unification was the existence of electromagnetic waves that should travel with this special speed, the speed of light or the speed of electromagnetic waves in vacuum. That was a major triumph, but also somewhat problematic at the time, because nobody up until that point had experienced waves traveling in anything other than some physical media. So if you think about different wave phenomena, it's not something we've covered in this course, but if you think about wave phenomena that you're familiar with, you're usually expecting those waves to be traveling in some medium. Maxwell and Maxwell's equations and the prediction of electromagnetic radiation tell us that waves can travel and do travel in vacuum. So that was pretty disturbing to people back in the 1860s, and many people were not believing this to be correct because they'd never seen examples of waves traveling in the absence of media. And so a lot of work went into this, and in particular a lot of experimental work to try and understand what was going on. Hypotheses, the one that was most prevalent, of the existence of some kind of medium, this one happened to be called the ether, that had to exist in empty space, so it wasn't really empty, and somehow had the criteria of being some medium in which a wave could travel, but also being a medium that had no mass, no density, no resistance, no viscosity, so not a consistent idea, but again, people were very reluctant to shed this idea of waves being able to travel, or only being able to travel in a medium. So, classic experiment, I can't remember exactly the date, I'm kind of imagining around 1889, was to try and detect the existence of this ether by using a device called an interferometer. I'm going to be brief on this because it takes some time to talk through it in detail. But again, partly because it's historically of great interest, but it also turns out to be the technique that's used in these gravitational wave observatories these days. What's an interferometer? It's basically a device that takes a light beam, divides it into probably two different beams. In this cartoon on the right-hand side, that splitting is performed by that kind of gray diagonal object, which is a half-silvered mirror. Means part of the light gets reflected, part of it gets transmitted. So it goes in two different directions at right angles. Those two different directions, up and to the right, are then there's a full mirror, a blue, those things in blue are fully silvered mirrors that reflect the light backwards to that, again, half-mirrored thing in the middle, where they're recombined. Okay? And they're recombined in a way that we can measure and see what the result is. So there's a lot in here which won't make sense, perhaps, until the spring in particular, for those of you who are carrying on in the spring, hopefully all of you. But what it allows us to do is to observe interference effects between those two light waves. Okay, so interference, again, something we'll talk about later on. It's the idea that waves, think of a sine wave, depending on whether they're in the same relative phase to each other, which is to say they're both two waves that go up and down at the same point. If you imagine two waves like that in phase, when you add them together, they do indeed add together, and you get a larger amplitude wave as a result. The other sort of extreme possibility, which is going to be hard for me to do in a convincing way, is you have two waves that are, let's say, exactly in antiphase, so when one wave is going up, the other one's going down. And in this case, when you add them together, you get zero. So what's called constructive and destructive interference, and then the thing I'm definitely not going to try, because it's like doing that thing, which I can't do. It's like when they're in some random relative phase, and they could be adding together, they could be cancelling out, so on and so forth. So the same thing is going on here. All right, so in this context, this was set up because the idea was, if there was such an ether, we're sitting here on the Earth, and it was known, of course, at this time that we're moving around in our solar system and moving around in our galaxy. So if an ether existed, the thought was, I could do an experiment like this. The ether, this red arrow up here, would be an ether wind, because we would be moving relative to this substance in our galaxy as we moved around the center of our galaxy. So the idea is that we're moving through an ether wind. And that in fact this ought to change the travel speed of light waves, in particular moving into or out of the ether wind versus moving sideways with respect to it. So a very clever idea, making use of a split beam of light, bringing it back together after it's gone in two different paths which are perpendicular to each other. In this case, the idea was that it would be a way to test whether the ether was real or not. So it's a famous null experiment, and the idea was also that you could rotate this and do various sort of checks and whatever they call those things in medicine, where you do a trial that you know is kind of your reference. Anyway, it was never discovered. The ether was never discovered, and in fact, eventually, based on this, people had to reject the idea of the ether, and in fact, recognize that electromagnetic waves could travel in truly empty space. So I said this is in the late 1800s, kind of feel 1889. Special relativity brought forward in 1905. So this is very much an idea that's feeding into Einstein's thinking, and eventually coming up with this idea that the speed of light is in vacuum, it is what it is, and it has certainly no need of any ether, but it also doesn't have any need, or it doesn't change depending on relative motions of sources and observers. So there's a hugely interesting history from the 1860s to 1905-ish of the development of ideas about space-time, light, and relativity through this sort of interesting story. And again, why did I show you this in the context of modern physics? This is exactly what these laser interferometric gravitational wave observatories do. This one, the original one was done, was about yay big on a tabletop. You can take this idea, amplify it by several orders of magnitude, and build these things that are several miles long now, and that's what these interferometers are. Their purpose is different. They're actually now sensing very tiny motions of those blue mirrors and using that to detect the traveling of gravitational waves, but the technology is the same, at least roughly speaking. Okay, so very important experiment, shows that in fact the speed of light is constant in all inertial reference frames. Okay, so what is particularly impressive about Einstein's achievements is a lot of his breakthroughs came from simply thinking about things in a way that's different than everyone else, trying to shed common preconceptions, and just imagine what things would be like if some of our day-to-day experiences, our day-to-day intuitions were thrown out the window. So think about this. Einstein didn't have any access to technology that really allowed direct observation of things moving very fast. These days, we're a little better able to sort of look at things that are moving fast, and maybe we would have empirical inputs to special relativity, but Einstein didn't. And the reason, as you're about to see, Einstein talked so much about traveling trains it took me a while to appreciate this, but at that time, trains were about the fastest moving thing in the world, okay? So that's why trains, I think, tend to feature in Einstein's thinking, but they're thought experiments, okay? Very impressive. So let's see how far we can get through this idea of simultaneity, time dilation, length contraction, and finally the Lorentz transformations. Hopefully we'll get a good way through. All right, simultaneity, the idea that things occur at the same time. So how do we define this? Two things are simultaneous if they occur at the same time in my coordinate system. Pretty straightforward. But if we have two different observers moving in two different reference frames, constant velocity, so they're inertial reference frames, they will not in general agree on this idea of simultaneity. And so it's not an absolute concept, and it's very much one that depends on the motion of the observers. So let's see if I can try and do this. I was lucky to inherit this from somebody, which is nice. I kind of feel like I do it a little better these days. But so here's one of the Einstein thought experiments, and it's very much set in the setting of a moving train. This is a train car, which is in a moment going to move from left to right. So let's see if we can set this up. Okay, train car. Somebody's inside the train car. They happen to be in the middle of it. So this is observer O prime in a moving reference frame. Once this thing starts moving, it isn't yet. And outside on the ground is another observer in that person's reference frame, and that person's on the reference frame of the ground. Okay, so these are clearly two observers in two different reference frames. And in a moment, this one's going to head off at constant speed to the right. So we're going to set this thing up so that these A's and B's are sources of light. Maybe they're flashes of light, things that will emit flashes of light. There's one at this point at the, let me say, the left side of the train car, and there's one at the right side of the train car. And then also, imagine this is maybe in the inside of the moving train car, a light source A prime and a light source B prime. All right, so we're going to imagine that we're in this external reference frame, we're observer O, and in our external reference frame, once these things go off, light's traveling towards us. Of course, it's traveling in other directions as well, but this thing is going to show you a couple of small red dots moving once I animate it. And that's supposed to represent the light coming from A towards observer O and B coming towards observer O. And I'm going to give this away a little bit. Let me make you focus on A and B and the little red dots that are light coming out of it. Here we go. Okay. So forget about the earlier or the later motion and forget about what's happening with A prime and B prime, but just once again look at what happens to the red dots coming from A and B. They arrive at O at the same time. That's our definition of simultaneous, okay? But we're claiming that we're also having light sources A prime and B prime fire flashes of light. But now we're looking at that from the perspective of the moving O prime observer. And light is supposed to be, according to the postulate, traveling at the same speed in both reference frames. So this is, I can't do a great job with this, but just take a look at what happens to the red dots in the prime reference frame, and in particular what happens to them compared to the O prime observer in the middle of the moving boxcar. All right? So I'm going to do this a couple more times. Now this is an extreme case, and maybe a bit too extreme, which is the reason I don't like it so much. But what's apparent right off the bat is that the arrival time of those two red dots for O prime is not the same. So they're no longer simultaneous. And again, I don't like the way I've set this up, because in fact, the light in this scenario actually from the left side never reaches O prime, at least the way this cartoon is run. So it's a very simple thought experiment. And again, this is very much what Einstein did, and you can see him writing these things down and describing them. It's It's the idea now that just based on the constancy of speed of light, in this simple example, the idea of simultaneity is something that is going to be observer dependent and reference frame dependent, okay? All right, so that's one thing. And again, this is all sort of a little bit hand-waving. We'll try and get a little bit more specific in the last 10 to 15 minutes and start talking about some actual observable effects, and we'll come back to this idea of simultaneity maybe at the end of today, or if not, on Thursday morning. So, let me now take this moving reference frames and light flashes and put it in a slightly different context. And unfortunately, we're getting a little bit hampered by